So one of the discoveries that we've made as part of modern physics is that light has what's known as wave-particle duality. Going back many centuries, there has been an ongoing argument about what is light made up of. Is it a wave or is it a particle? And what we understand now is that light can be either. In some sense, light will act like either a wave or a particle depending on the situation you put it in. But before the era of modern physics, there was this ongoing debate among scientists about what light was, particle or wave. Newton himself thought that wave was actually made up of particles. He called them corpuscles because Newton was a big fan of using different words than what we do now. But his idea was that light was made up of particle-like things. There were others, notably Hooke at the time, others who would follow after, who said, no, light is a wave. And it was an ongoing debate until a couple of experiments came along in the 1800s that convinced everyone, no, it's pretty clear that light is a wave because we see interference. And the first of those experiments was the Young's double slit experiment. And so what we're going to introduce here are the basics of that experiment and then why it was such powerful evidence for the idea that light is a wave. So what's the setup for this experiment? Well, we have an incident wave that's coming in, and all we're going to do is basically we've got some barrier, so the light can't get through this, except we're going to make a tiny little hole. And what the tiny little hole does is it simply says that we're effectively taking all this light out here and turning it into a single source. So the light, as it passes through this hole, will propagate outwards. This hole is going to act like a spherical source, which is why we've changed and now these look like circles or circular arcs as the light moves off from our initial source here. But what that does is it ensures that whatever gets to this second barrier is in phase. So sort of reducing everything over here from our initial incident wave down to a single source guarantees that whatever is coming through has to be in phase because it's all coming from a single source. But now what we're going to do is we're going to, in this second barrier, create two holes. And so what we've done is we've created a single source of light and we're going to split it to make two sources. So what we have is two source interference. So we're going to have light coming away from source 1, light coming away from source 2. And so what you see when you look at some screen over here on the right is the interference pattern that we've been talking about over the last several sections. So when you look along the middle, you see a maximum. Light adds up, but it falls off, and you end up with a minimum, where the light from our two sources cancels out. It builds back up, we get another maximum, falls off to another minimum, and so we have the interference pattern that shows us these alternating maxima and minima all along our screen. So at the time, this was the clinching evidence for why light had to be a wave, was because only waves interfere. Waves care about phase the way that nothing else does. Interference cares about phase because it's adding up waves. So if light interferes, then it has to be a wave. So if we take that screen and look at the pattern, along the center line, we see a maximum. And we know that that maximum corresponds to the fact that the path length traveled by the waves from each of those two sources is the same. So the path difference is 0. As you start to move away from the center line, however, what we see is the same sort of behavior that we've talked about before with two-source interference, is that you get your maxima when the path differences are an integer multiple of the wavelength of the light. So here we see the first maxima on either side of the center line correspond to a path difference of 1 wavelength. The next maxima out correspond to a path difference of 2 wavelengths. After that, a path difference of 3 wavelengths. So the maxima are defined by a path difference equal to some integer number of wavelengths. The minima are also defined by a very specific path difference between how far your wave travels from one source and how far it travels from the other. So for your first minima on either side of the center line, the path difference is half a wavelength. That half wavelength path difference is why they line up in such a way your waves cancel each other out and you get a minimum in your pattern. The next minima occur when the path difference is 1.5 wavelengths, then 2.5 wavelengths, then 3.5 wavelengths. And so again, it's that additional half wavelength, so a whole integer value plus an additional half wavelength that causes minima. So if we want to figure out how to take advantage of the fact that we know what that path difference is, let's come back and look at those two slits that we're using to create our two sources. Those two slits are separated by a distance d. The one big difference between this problem and the two source interference problems that we may have worked previously is that we're going to assume that the screen onto which we're projecting is far enough away that we can treat the light coming from both of our sources as traveling parallel to each other. So notice that the angle that both of these rays make, so the ray from source 1 and the ray from source 2, they both make an angle theta with the horizontal line traveling straight over to where our screen will be over here on the right. That's the one big difference. And the nice thing is it simplifies the math. And so if this is the angle theta, then that means that this angle sitting in here is also theta. And so what that gives us is a right triangle where D is the hypotenuse. So the distance between the slits is the hypotenuse. This is an angle theta, and the opposite side to that angle theta is the path difference. So this little distance here, this side of our right triangle, is how much farther the light coming from source 2 has to travel than the light coming from source 1. So I can relate theta, d, and the path difference by using this right triangle. And so what I see, of course, is that the sine of theta is going to be the opposite side, that's the path difference, over the hypotenuse, that's the distance separating the slits. And so this gives me a simple equation that says the path difference has got to be equal to d times the sine of theta. Since I know what those path differences are for my maxima and my minima, that means I can set up two equations. My maxima occur at points of constructive interference where the path difference is 0 along the center line, and then 1 wavelength, 2 wavelength, 3 wavelengths, so integer values of the wavelengths. So I can set up an equation that will show me where I'm going to get points of constructive interference. So d sine theta equals, and we'll choose to use m here, so m times lambda, where m can be 0 if I'm at the central maximum, or 1, 2, 3, 4 for any of what often get labeled as bright fringes. So we call them fringes because they're not sitting on that center line. And so if you want the second bright fringe, this equation's set up to say, oh, the second bright fringe means you want m equals 2. The minima, those are going to occur at points of destructive interference, which I know means I've got an integer value plus an additional half wavelength. So half a wavelength is the first option, 1.5 wavelengths, 2.5 wavelengths. And so again, I can set up an equation where d sine theta equals, and all I've done is I've picked a different number, so we're going to use n here because it doesn't start with 0. And then notice I've set this up so that n minus 1/2, and n's first number can be 1. 1 minus 1/2 is 1/2, so that's my first value. So the first dark fringe corresponds to n equals 1. The second dark fringe is n equals 2. So I've got two equations here, one of which gives me the maxima in my pattern. The second one gives me the minimum in my interference pattern. The other detail that I can take advantage of course, is that for any point on the screen, there's also the distance from my slits to the screen. So notice in this picture, My two slits are basically so close together that they're dwarfed by this distance L. That's why I can treat this as a single angle coming from both slits theta. But what you'll notice is that L and Y also are the two legs of a right triangle defined by the angle theta. And so I have a second equation I can use that says the tangent of that same angle theta that we were using in our equations for the minima and maxima in our interference pattern has also got to tell me where I am on the screen. So I'm some distance away from the center line. That's what our value y is here. And L is the slit to screen distance. So this gives me three equations. One describing what's going on for the minima, one that describes what's going on for the maxima in my interference pattern, and a second one that's telling me about how far away my screen is, and so therefore how far my points are from the center line. Those three equations are what I'm going to use to solve my double slit interference problems.